Hello and welcome back. In this video we'll be talking more in depth about graphs of functions of two variables. Remember in the last video I showed you the graph of a function of two variables, and our visualization technique for these things are to treat the outputs of our functions of two variables, f of x, y, treat those outputs as our z-coordinates for the set of points x, y, f of x, y. So just to remind you of this, I'll jump to what I showed you in the last video. So remember, our domain is some region in the xy plane. For each point in that domain, we have a function output for that point. And so we mark the point xy, f of xy, and that gives us a point on the graph of our function of two variables. When we do this for every point in the domain, we end up with a surface that hangs either above, like in this example, or below, or some combination of both, above or below our domain. So that's the idea. We treat these functions, the graphs of these functions, as surfaces. That's how we visualize them. So remember, just because the graph of a function looks like a surface, it doesn't mean every surface in R3 can be a function, or the graph of a function. So compare this to, say, something we did in Calc 1, which was we looked at a circle and asked ourselves, you might have done this in a pre-calc class, asked yourself if this was a function or not. So here I have a circle. Actually, I changed this. This is an ellipse because I have A and B here. These could be different from each other, in which case we'll get an ellipse. And so we can ask ourselves for a function of one variable or rather we ask ourselves for this curve in R2, is this a function of one variable? So you may remember an example like this, and you may remember doing something called the vertical line test, right? We can check vertical lines, so lines parallel to the y-axis, right? The idea is we want to generalize from things we already know up to 3 dimensions, up to functions of 2 or more variables. So in the case of a function of one variable, we have the vertical line test. Remember that we need to check every line parallel to the y-axis and check if it intersects our curve more than once. If there exists one line that intersects our curve more than once, then immediately our curve is not a function of a single variable. So this one, the circle, right, we can see some lines here. This one intersects twice. There's some that don't intersect at all. There's some that intersect exactly once. So again, the idea is we're looking for at least one line that intersects the curve more than once, strictly more than once. And then we can say that the curve is not a function of one variable. And remember, we can play around with this equation, right? If we want to make this try and look like a function of one variable, we want to get y in terms of x. So one thing I can do there is I can sort of subtract x squared over a squared. I can get y squared. I'll multiply the b squared over b squared times 1 minus x squared over a squared. And that's pretty good. I have y squared equal to this. And then remember, the problem comes in here when I take a square root, because y could be both positive or negative. And so when I take a square root of both sides, I'll end up with y equals either plus or minus b times the square root of 1 minus x squared over a squared. So it's this plus or minus business that really messes up algebraically and further clues us in that this is not the function of a single variable. So this actually gives us two functions. And when we combine them, so we get, let's say, y1 equals b square root 1 minus x squared over a squared. And then let's say y2 is b minus b times square root of 1 minus x squared over a squared. So if we put both of these functions together, we get the graph of a circle. So if we graph both of these functions, we end up with the full curve, but the curve itself is not the function of a single variable. It's not a single function. Right, so yeah, just kind of recall how we did this in 2 dimensions for functions of one variable, and now we're going to extend to 3 dimensions. So while we had the vertical line test in the example we just saw, really what was going on is we were looking at lines that were parallel to the y-axis. So that was a vertical line in 2D. This was a line parallel to y-axis, to y, and that was our output axis. In 3D, for a test for a function of two variables, we want to look at lines parallel to the z-axis. And the same thing is true here, only we're looking at, does any line intersect the surface at more than one point? That's the idea. So let's go ahead and take a look at some known surfaces. We have all these quadric surfaces that we developed at the end of chapter 13 that now we can study and ask if they're functions of two variables or not. So we'll take a look at ellipsoids. We'll look at the general form for ellipsoids, elliptic paraboloids, and hyperboloids of two sheets. They'll all be oriented in the same sort of way, right? Z in terms of x and y here. And we'll go through each of these and ask ourselves if it's a function of two variables or not. So for the ellipsoid, I'll remind you of our equation for an ellipsoid that generates the ellipsoid. Remember, the set of all points x, y, and z that satisfy this equation gives us an ellipsoid that looks like this. I'm going to go ahead and jump to an interactive figure with that, and we'll ask ourselves, can we find a line parallel to the z-axis which intersects the surface, the graph of the surface, more than once? So here I have a line parallel to the z-axis that does not intersect the surface at all. All right, so there's at least one line that doesn't intersect the surface. Maybe I'll jump here. That also doesn't intersect the surface. I better move my x in a little bit closer. There is a line parallel to the z-axis, which intersects twice, if you can see that. And so immediately then, if we are trying to think of this as a function of two variables, that point in the domain, so imagine the shadow of this thing, it's an ellipse, of course it should be, that point in the domain would have two corresponding points in the codomain that it maps to. And that's not a function, right? How would we know what the output of that function is if there's 2 points that are associated with it? So that tells us this ellipsoid is not a function. In general, ellipsoids are not functions of two variables. So let me jump to that. And I did the ellipse example, the ellipse example I just did down here, because we can do something similar for the ellipsoid. So rather than just saying, yeah, this is not a function of two variables, what we can do is we can actually find two functions, just like we did for the ellipse here, that generate the surface here. So I can do the same thing that we did there, and that is now, since z is my output variable, I'll try and solve for that. So I get z squared equals, looks like I'll have c squared times 1 minus x squared over a squared minus y squared over b squared when I just move these things to the other side. So I almost have z, but now, right, if I try and take a square root, z could be either positive or negative, and so I end up with two functions. I have z is either, so maybe I'll say z1 is c times square root 1 minus x squared over a squared minus y squared over b squared. And z2 will be minus c times square root 1 minus x squared over a squared y squared over b squared. And so again, I need two functions. So I could call this one, say, f1 of xy and f2 of xy. So we need two functions to give us the graph, or rather to give us the ellipsoid surface. So no, an ellipsoid is not the function of two variables, but we can find two functions that give us the surface. Let's move on to the elliptic paraboloid. Well, it'll look something like this, right, with the form that I have. We can ask ourselves, is this a function of two variables? So again, jump up to this three-dimensional analog. Consider lines parallel to the z-axis. I think I can do this in our interactive figure here. I'll jump to elliptic paraboloid. And we can ask ourselves, are there any vertical lines that pass through the surface more than once? So there, that one passes through once. Remember, we could zoom out here. The thing's going to continue, but in the same sort of way, right? We have ellipses the whole way up, parabolas and the other two traces. Right, and so after thinking about this for a little bit, we should be able to convince ourselves that no vertical, or rather line parallel to the z-axis, will intersect this curve, intersect this surface in more than one spot. And so the elliptic paraboloid it passes the vertical line test. It is a function of two variables. And one really easy way to see this with the algebra is that the elliptic paraboloid, our equation that generates the elliptic paraboloid, is already in terms of z. And so just setting f of xy, so defining our function now, equal to x squared over a squared plus y squared over b squared, well then, with z equal to f of xy, we have exactly the elliptic paraboloid. So I'll say check, yes, a function of two variables. This one, the ellipsoid, was no, not a function of two variables. We can ask ourselves about the hyperboloid of two sheets. Again, we'll examine the geometry as well as the algebra. And here, pretty clearly, if you just look at the z-axis intersects the surface at 2 points. And so immediately, it's not the function of two variables. So we can say no, not the function of two variables, but we can ask ourselves, can I get, say, two or more functions that together give us this surface? And certainly we can. We proceed in the same way we did with the ellipsoid. I'm going to try and isolate my z variable. So I'll jump a few steps here and say z squared is equal to, what do I get over here? I'll have c squared times, it's a little different than the ellipsoid, right? Because these are negatives over here, so this will be 1 plus x squared over a squared plus y squared over b squared. And then I can take a square root, but remembering that when I take a square root, I get either positive or negative output, and so this gives me two functions again, the positive version and the negative version. And so again, I have two functions. I need two functions in order to generate the hyperboloid of two sheets. So you could ask yourselves the same question for the rest of the quadric surfaces. Think about a hyperboloid of one sheet or an elliptic cone. And you can ask yourself for all of those, is this a function of two variables? Run the vertical line test, try and convince yourself. And then as a last step, try and find the function, or if you can't find a single function, if it's not the function of two variables, try and find a collection of functions that together produce the surface, just like we did with the ellipse in 2 dimensions. All right, that's it for this video. I'll see you next time.